to introduce André Schleife, as associate professor in the Department of Material Science and Engineering. He has a wide-ranging research interests, in computational material science, and also now moving into the use of quantum computers to do calculations of materials structure, electronic structure, properties. This work is actually also a part of the IBM Institute, the Discovery Accelerator Institute, and I think we'll hear about that in collaboration with the IBM researchers at Almaden. So, okay, looking forward to your talk, André.
Great, thanks, David. Thanks for the introduction. Thanks for coming to the presentation. And in fact, this is an example, and you'll see an example, the second example for where by working with David, I got into a completely new research direction. So this one is, mostly preliminary work, but it is sort of like our state of the art, what we're doing in my group on using quantum computers, and I'll quantify that in a moment, to study material science problems. This is my group, and I'll start off by acknowledging the people who actually do the work. And today you'll see mostly results by Vijaya, who's a postdoc in my group. She's right over there. And Yiting, who is a grad student, and I don't know where he's, somewhere in the audience probably. Yiting is over there, yes. So these are the two guys doing the work. And as David said, it's a project with IBM. So Barbara Jones is our IBM collaborator. So she's at IBM Almaden, and we work together. The next person on the team is Santiago. So he helps us whenever we're using the local, or not local, the IBM quantum machines. So Santiago has access to them and can help us manage these sometimes issues that occur when we're running on the machine. And then also through the IBM project, we worked with 3 undergrads, Yufu, Sarah, and Pedro, on related topics in this quantum computing field, I would say, but I didn't put any results today. I just want to acknowledge that contribution. Okay, the work is done and funded by the IBM Illinois Discovery Accelerator Institute. All right, so let's, the way I'll start about this topic is I'll briefly explain in one slide, because it's, again, that's not my work, it's mostly from the literature, but I want to briefly say where we are with making quantum computers so that you can get some idea what the challenge is in using them. Now, in this case, I draw on John Prespill's paper who talked about this NISQ. You saw this acronym in the title of my talk, which is the Noisy Intermediate Scale Quantum Area or era. So this is sort of where we're right now. So when I say right now, the slide was from last fall, but it roughly gives you an idea what exists in terms of hardware, at least back when I looked at that. So the state at the time was that over the next few years, now by some loose definition of few, you will have something between 50 to a few hundred qubits. Again, it depends a little bit on the details on how you define a qubit and things like that. And I don't want to get into those fine-grained topics too much, but the main message is that having that is already what is really accessible beyond brute force simulation. So in other words, if we have such a quantum hardware on that order, wherever you pick exactly your number, that allows us to explore the hardware in a way that brute force simulation does not really straightforwardly allows us to do. Okay, so that's sort of like where we are now, right now. And one example that actually appeared pretty much a year ago is this 433 qubit IBM quantum device there, which is based on superconducting qubits. So this is also more or less the architecture that we're using for the work that you'll see in this presentation, right? So we use IBM hardware, and they use superconducting qubits. There are other techniques that exist, and again, I will not talk about those in detail. There are trapped ion computers and annealers, and all of these hardware implementations are being developed maybe at the same time. And it's not really clear yet maybe which one will win. I don't know. This is not exactly for using these IBM computers. Now, the other caveat I should say is that noise is a tremendous limitation. And in terms of making that more clear, all the machines that we have right now suffer from noise, and there are techniques to try to mitigate that. I will show you some of our efforts towards using those techniques, and I will show you what noise looks like when we actually run the simulation. So in other words, how does our data suffer from noise? I'll give you examples for that. So that still applies. The other caveat I just started talking about is that none of these simulations that you will see today that we do run on these IBM machines are run on those IBM machines because they're faster or better than what you can do in a classical computer. Okay, so this is exploratory, and in fact, it is. The goal is, I think, I would say is twofold. Number one, to sort of explore if we have better quantum computers, so maybe more qubits, maybe less noise, and so on. What could we do in material science or chemistry or physics, and how would we do it? So that's maybe one direction, and I'll give you some examples for that. And the other one is, how does noise affect this, and how can we mitigate noise? So it's really exploratory to see how this hardware behaves, I would say. Okay, and then this is maybe a general comment that quantum information is more than just quantum computing, so there are many other aspects to it, but I will not talk about those today. Before I now show you some actual results, I'll briefly talk about why we're doing this work in the first place. And to that effect, I have this slide here that shows you essentially one of the research directions in my group. So we're interested in understanding optical properties of materials, right? So I'm like David in the materials department, right? So there's always a question around actual materials, and both historically and currently, my group has been trying to use and develop techniques that can predict optical properties of materials. So predict meaning by parameter-free simulations, we get results that we then can compare directly to experiments. So there's no fitting, and we try to predict. Predict sometimes means that the experiment already existed and we compare to it, but that's the idea. And so some applications for those types of properties, I put them on the slide. This is kind of an older one where we looked at titanium dioxide, which is a material that has a gap larger than visible light, so like 3.2 or 3.4 electron volt, meaning it's transparent normally in an ideal crystal. At the same time, this is a material that's used as a photocatalyst, so you do want to absorb sunlight, right, which is of course visible. And so making this material less transparent, and in this case through introduction of sulfur, can make it absorbing the light energy and then hopefully use it for photocatalysis. So this is an example where this image is actually completely produced by simulations, meaning we ran the atomistic simulations first for different sulfur concentrations, produced optical spectra, and then stuck these optical spectra in a ray tracing software that generates the image. But the idea is that we want to predict, how does a change in this case, sulfur content change the optical properties of a material. Okay, another example is this photovoltaic material that we worked on mostly in the past. I think currently we're not looking at this anymore, but the question there is, again, how much light and in what wavelength range does the material absorb if you want to use it as a photovoltaic? And then what mechanisms are involved fundamentally? So by mechanisms, I mean in specifics, excitonic effects and dielectric screening effects in this material. So these are cases where our simulations can give us insight into the mechanism of optical absorption. And the last one, I'll show you that here. This is a work jointly with Andrew Smith in bioengineering. So he's an experimentalist. They make semiconductor nanocrystals out of cadmium selenide. They can make them, I can zoom in here a little bit. They can make them in both zinc blende and wurtzite structure. And what they want is, what structure did they make, right, in their nanocrystalline in solution samples? And they want to do that quickly, right? Of course, you could put that material somehow into an X-ray analysis and things like that. And without being experimentalist, I'm mostly quoting Andrew Smith when he says that these techniques rely on vacuum, and this is not really compatible with solution-based nanocrystals. And so what he wanted to is to relate this structural feature of zinc blende versus wurtzite to features in the optical spectrum. Okay, and so again, we simulated the optical spectra because we can impose any crystal structure we want in our simulations and identify that there are peaks at these energies here between, I don't know, 4 and 5 eV maybe, that uniquely correlate with whether the material is zinc blende or wurtzite, and that can then accelerate this phase distinction in experiment. Anyway, so I hope at this point you sort of believe me that looking at electronic and optical properties has various applications in materials, and that's the motivation, I would say. You can also ask the question, well, do we need these quantum computers? And the answer is, of course, no. So far not, right? We want to need them, and we'll hopefully get there. But all of the stuff that I just talked about, we have been doing, and many other people before us and in parallel with us have been doing on classical computers. So quantum simulations, but on classical computers for many years. And so I'll briefly show you those techniques just so that you can see what sort of like a success case sort of looks like today, right? Before you go to the quantum computer. Again, keep the caveat in mind that the quantum simulations we'll be doing are not faster than classical simulations. So the classical ones are still our comparison point. Anyway, so what we always do is, and you'll see this, I think, in at least one other diagram in this talk. When we study a material, we start with the crystal structure. For that, we typically use density functional theory in maybe various flavors, depending on whether you have van der Waals systems or not and things like that. But in general, we use density functional theory and obtain a ground state geometry of a material. So that can include defects, it can include surfaces. You'll see some of these examples in a moment, but that gives us where the atoms are in the system. And then we use these more expensive and more sophisticated technique to look at first the electronic structure. And we'll do the same in this presentation when I talk about the quantum simulations. So the first thing that we want to understand on the way towards predicting optical properties is the electronic single particle band structure of the material. So meaning valence states and conduction states. And for that, we use sort of like a series of techniques where you have sort of like a range between computational accuracy, starting at the density functional theory level, and then going all the way to many-body perturbation theory. And the way I said it right now increases accuracy and computational cost, right? And so what that looks like in practice, I will not talk about too much these equations right now because we want to get to quantum in the end. But if we start with a density functional theory simulation for a semiconducting material, what you see is, and that's very well known, the gap is too small, and D states are too high energy, right? So the gap in this case is maybe 0.7 versus 3.4. The exact numbers are anecdotal for the purpose of this talk, but it illustrates the order of magnitude of how wrong this can be. Okay, so that's the first step. Then we make one step towards this many-body perturbation treatment by exact exchange interaction in our description of the electron-electron interaction. So we go away from a very simple exchange correlation functional to a more sophisticated but computationally much more expensive one. In this case, this is a hybrid functional that gets our band gap closer but not on top of experiment. And then in the last step, we do this many-body perturbation theory where we correct this this hybrid functional band gap here of 2.1 eV, and we get maybe close to 3.2 or 3, which is maybe within 0.2 eV of experiment. So not so much to bring, again, I'm not trying to advocate for methods here or anything. I just want to give you guys an idea what can one expect from simulations that are currently used if you want to predict these kind of properties, right? And for band gaps specifically, I would say something like this is not unusual, right? You can maybe sometimes within 0.1 eV, sometimes within 0.4, but you get close to gaps typically by using a carefully, by building these methods carefully on top of each other and understand what each one does. You usually get relatively close to experiment, I would say. I'm not saying there are no counterexamples, but that's sort of like the state of these simulations. So at the end of that, in this case, this technique, but again, that doesn't have to be this one, we usually end up with an electronic structure that gives us a more or less reliable band gap and also band dispersion of all these other states in the band structure, right? So occupied and empty states, potentially including defects and things like that. Another order of magnitude, so for if you're not so much interested in these detailed methods, but you can at least take home that number. So these types of simulations, I think nowadays one can do on a couple of hundred of atoms max, right? So the exact expense depends not on the number of atoms, but the number of electrons. But anyway, a couple of hundred atoms is what can be done, right? And is done typically. All right, so that gives us the electronic structure. Now we want to look at optical properties. And for that, we follow this many-body perturbation theory approach where when we do an optical excitation, we create an electron into the conduction band. And this electron is then in the conduction band, the hole is in the valence band. So these two oppositely charged carriers interact. The action. Again, none of this is invented by us. This is in the literature for a while. And if you then go into this, if you follow this many-body perturbation theory treatment, this is a two-particle excitation because you have the electron and the hole. And the equation that describes that within many-body perturbation theory is this Bethe-Sapir equation. Okay, so that is also, I would say, a standard technique in the literature nowadays. One of other, it's not the only one that you can use to study optical properties, but it is one that you can use, and it specifically accounts for this electron hole, the optically created electron hole. Just as for intuition, in these previous experiments, when you measure single particle states, for instance, through photo emission, the excitation energies are much higher, and there is no, if you do photo emission, you emit an electron into vacuum. You're not just exciting it into the conduction band. So that's the difference between a single and a two-particle excitation. Okay. Anyway, now, right. So there are problems in the details, but we can discuss them maybe after. All right, so we solve this Bethe-Salpeter equation. This is what the equation looks like with this shorthand notation. So it's an equation for the polarization function of the system, and the crash course is essentially so this is the equation we would like to solve. In reality, we transform that into an eigenvalue problem for this Hamiltonian. That maybe it's a bit blurry. It's actually more blurry on the projector than on my screen. Anyway, so this Hamiltonian is what we call a two-particle or an exciton Hamiltonian, which looks at conduction and valence bands, and it's for optical excitations where we're vertical in K-space. And so this is a Hamiltonian that has the band structure on the diagonal. So these epsilons here are energies of our states that we computed up here. And the delta functions make it diagonal. And then we have these interaction terms. This is the Coulomb interaction between electron and hole. Again, so this is implemented. We have contributed to certain developments in this context. Again, I will not dwell on that too much, but that's the technique that we're using. And what I want to spend the next 2 slides on is to show you what that does, or what the effects of these excitonic effects are in the spectrum. So the example here is magnesium. It's from an old publication, but it's a nice system that shows the basic effects that occur. And the target quantity that we typically compare to can be either optical absorption or a dielectric tensor. So the imaginary part of a dielectric tensor as a proxy to optical absorption. And what this figure here shows, just because of blurriness, I'll zoom a little bit. What this figure shows is essentially 2 curves. One is the curve that we would get if we do everything I said until now, meaning hybrid functional and GW and all this kind of stuff to get correct band gaps, but we ignore this electron-hole interaction. Okay, so what you see in that case is this red curve, and the gap, not so bad, right? Kind of close to experiment, but that's it, right? So everything else looks not so much like experiment. Black is experiment in this case. And so then the reason in this semiconductor or many other semiconductors are excitonic effects. Okay, and so what we then do is we solve this Bethe-Salpeter equation, and if the only change we do is what I just said, right? We include this electron-hole interaction, everything else unchanged, is this change in the spectrum, right? So you see a tremendous change going from red to blue. So there's 2 effects that I always like to emphasize, because again, these are not just happening in magnesium oxide, they occur in many semiconductors and insulators, which is number 1, you get this bound exciton here at the onset, and so this is absent here, but it's present if you have excitonic effects. This is sort of like at the band edge, the lowest possible excitation of an exciton comes with very large oscillator strength, which is why this peak is so high. And then the other effect that you oftentimes see is these redshifts. So I label it for this peak here, but you see similar effects here, maybe here. So this is also something that you see for many semiconductors, that excitonic effects affect optical spectra and higher energy range by redshifting, so meaning left on this energy axis, peaks from a spectrum that does not include electron-hole effects to a spectrum that does. All right, so that compared to experiment, again, this last is maybe the only thing that you really could keep in mind. So something like this, where we more or less reproduce peak positions pretty well, give or take, and peak heights, again, give or take, that is something that we would call good agreement, right? So just so that you have some baseline. So if you look at this and think this is bad agreement, it's not going to get better than that in the work that you'll see today, right? And at some point, and that's something we've started seeing more and more, there are also examples where the experimental peak heights, especially peak heights, is very difficult experimentally, right? If you do ellipsometry, peak heights, they have a bunch of models that they stick into, converting the data that they measure directly to the spectrum they publish. Go ahead, Jim. Yes, the oscillator sum rule. Yes, so the total integral has to come up with the plasma frequency divided by cell volume, something like that. Yeah. Well, so but the sum, yes, but the sum rule would then apply, I think, for the real part. Are you talking about chronic? Overall integral. Well, I see. So 2 comments. So I think number 1, one parameter on our simulations is the number of empty states, and that is a fixed number, and our spectrum will only be accurate up to whatever that number is. So what you see in this figure, so we have enough empty states to show this plot, but anything above, we go down to 0, where our experiment might not. And then the question, I don't actually know if they enforce or applied any sum rule for the experiment. That's also a good question. But in general, yes, there is some rule, and our simulations obey that sum rule. Yes. Okay. Anyway, so this is something that call good agreement for optical properties. All right. And at this point, I will now come towards how can we now, if this is what you want to do, more or less, how can we use quantum computers for that? Okay. And so by we, I'm not just talking about our group, even though the examples you'll see will be mostly from our group, but I also show you a couple of other examples from other groups, just so that you get an idea what sort of like the field is doing. The caveat of this is moving very rapidly, so this changes a lot. So maybe view this as a snapshot that is maybe kind of true when I made the slides. Anyway, so applications of the manifold, but in chemistry, material science, and also in physics, really, in the field of physics that my group is working on, what we want to typically do is we want to solve Hamiltonians, meaning finding their ground state and maybe the total energy of that ground state. We want to compute observables, and we potentially need more than the ground state, which is excited state simulations. That's what you just saw on the previous slides. Those are mostly excited states. So the goal in this field is sort of like around that. And the question is, how can we use quantum computers to do these kind of things? And that's what I'm giving you examples now. There's an interesting question by Garnet, and I'm trying actually to get him here to exactly onto this stage. I've tried many times, and we're close to scheduling him. I don't think we have quite nailed this down yet. But he asked the question, if this argument that there is exponential quantum advantage using quantum computers, that's actually not so simple. Now, again, the details, if you're interested in this kind of question, you can look at this paper of his. I think it's probably published by now, but you can ask, well, will there ever be such a quantum advantage or not? Anyway, for now, we're assuming there will be, and we do need to develop quantum computers, and that's under that presumption, you'll see what can be done. There are also other things that you can do in our field that you will not hear about today, which is, for instance, people use machine learning combined with quantum computing and things like that. We have not explored this at all, right? So we're looking at solving Hamiltonians, computing observables, and potentially doing that also for excited states. One of the things we did look at with undergrads, with Pedro, for instance, and Sarah, is this time evolution question. So all the things that you saw so far were kind of static in time, right? We look at a absorption spectrum or something. There was no real time dependence. People also work on that, right? So there is developments in that field if you want to do time evolution. Not today. Right. So the first thing that we're facing, if we have a quantum computer that has 433 qubits, like the one by IBM, the problems that we're typically solving when a couple hundred atoms, maybe 100, 200, 300 atoms, are too big. Okay, so we're not going to put those on a quantum computer. Or to be more technical, the Hamiltonian that you saw, this excitonic Hamiltonian that you saw when I pointed it out briefly, in our simulations typically has ranks on the order of 50 to 500,000. So that, again, there is a range because it depends on the material and K points and all this kind of stuff. It's a high rank, like a large rank matrix. That is too much to put that on a quantum computer explicitly right now, right? So we cannot simply do that and expect that to work. And so what people use, this is one example of a technique that's used, is an approach called quantum embedding. We didn't invent it. In fact, it was not even invented for quantum computers, as you'll see in a moment. But the idea there is that your entire system that you want to study can be somehow decomposed into an active space and an environment. Okay, and what you then want to do is you want to use a highly accurate technique, and in the past that meant quantum chemical methods on a classical computer for your active space, and you want to couple that somehow to the environment that you solve with a much lower accuracy technique. Okay, so I'm saying coupling somehow because there is not just quantum embedding approach, right? So there are different ways of doing that. One is density functional embedding, where the single particle electron density is used to achieve this division into active space and environment. And then the idea is, so this is most closely related to what we're doing. Quantum chemical wave functions, and DFT is used for the environment. So that is now something you'll see I'll show you a couple of examples in a moment, but you see that happen in the literature more and more. Sorry for the blurriness of this plot. Yeah, look, this is what I meant. Okay, so we have active space, we have environment, and it's somehow coupled. This picture is from a paper, I'll give you the reference in a moment, where they use the dielectric response function to achieve this coupling. But again, so I think there are techniques, and if you want an overview, I would probably recommend starting in this paper, but you know, your mileage may vary. Other options include this Green's function embedding method, where the Green's functions are used to achieve this decomposition, or density matrix embedding. Again, we're not experts in all of these different techniques, but that's the bottom line of the slide. Is I would say that this approach in general is used to reduce the problem size that you want to treat explicitly on the quantum computer. Okay, so examples of where this has been done in the literature. Again, I think if you guys are interested in reading more about this, this would be 2 pointers, I would say. So number one, not so unrelated from what we're doing, meaning chemistry on surfaces. So this is, in this case, I think they're looking at magnesium oxide at the surface of magnesium oxide, right? So this is already a big system in terms of numbers of atoms. And what they did, now it depends always, for each of these papers, it depends on the details. So they divided into active space and environment based on electron density differences. They use these coupled cluster single determinant natural orbitals in their basis. It gets technical very quickly, and the results depend on these technical choices. But the bottom line is that by doing this quantum embedding technique and using a very high accuracy for the active space, as opposed to density functional theory for the entire system, they did find that a reduction of the reaction energy was found compared to DFT. So again, this can be completely done classically, right? You can do quantum embedding and do a quantum chemical approach for the active space and find the same result. In fact, that's usually the point that you're comparing your quantum computing calculations to. But anyway, this is here just to make the case that this quantum embedding can lead to higher accuracy. And then what they did is they used not just some quantum chemical technique, but they performed this VQE, so a variational quantum eigensolver. I show you that on the next slide, to do simulations on the actual quantum computer. All right. You'll see this is also super typical and common in this field nowadays. If you want to do sort of like material science with quantum computing, many people perform this. Not everyone. There are other alternatives. You'll see that on the next slide. Another example are single molecules, where you know, a Hartree-Fock and a DFT scheme were used together with a self-consistent update of the embedding potential. So this kind of tells about their approach to achieve this quantum embedding and the coupling between active space and environment. So they separated into these two systems based on a range separation technique, where DFT is used for short-range interactions and wave function-based methods for long interactions. And then they looked at various different molecules. And you'll see again that they use this VQE technique, so this variational quantum eigensolver. I don't know if I can move this mouse away. Okay, this one. All right. So what does this do? Okay, so let me briefly give you an idea of that. So this is a variational technique. And the idea is that this is a technique that allows us to find ground and excited states, sometimes even of electronic structure problems, on state of the art. So this noisy intermediate scale quantum hardware, it uses that hardware, and it solves sort of like a variational problem. So what does that look like in practice? So just like any variational problem, the idea is that you come up with wave function ansatz that depend on parameters, right? It's a variational ansatz, so it's just like that. And then what you do is two things. You evaluate this expectation value on the quantum hardware as your wave function changes, and a classical computer changes the parameters of these wave functions. Examples for wave function ansatzes I'll give you in a second when we talk about visual explicit calculations. But that's the idea. So it's a variational ansatz, and it combines you know, this classical optimization of the parameter of the wave function with an evaluation of the expectation value on a low depth quantum circuit, so not so many qubits, in other words. Now, this statement, I would say this may be my personal opinion based on the literature. So this is more or less widely used in that community approach. It seems affordable by some measure and efficient by some measure. Again, it's not the only technique that you can use, but many groups do. So maybe yeah, I'm not sure if I should endorse it or not, but I'm just saying the reality is many people use it right now. Okay, and it seems to be more resilient to errors that occur, control errors in this case, than so-called quantum phase estimation schemes. Other caveat: we didn't compare all these different techniques, right? I'm just quoting from the literature for this. We use this VQE and that's it. Okay, as I said, other of these hybrid algorithms exist also in the literature. But again, this is a good starting point if you want to see what people do when they do electronic structure, including quantum hardware. Okay, so this is now the example. I think this is maybe the first example that I personally have seen. I don't think it was necessarily the first one in the literature, but where the group of Julia Gully in Chicago, they started looking at NV centers. So NV center is a nitrogen atom and a vacancy in diamond combined together. They also looked at these silicon vacancy centers. And the idea is maybe best summarized in this flowchart before I talk about the points on this slide. It goes sort of similar to what I talked about when I showed you our classical computing electronic structure methods. You start with an atomistic structural model of the material. So that needs to still come from somewhere, and somewhere usually meaning DFT. The atomic structure is done outside of this whole quantum computing scheme right now. So you start with that, and then you do your quantum embedding, meaning you have to divide your system into active space and environment. A specific example of how this group does it, I'll show you also in the next slide. And then what they do here is they run this VQE, for instance, on quantum hardware, and they compare to a classical, so quantum simulation on a classical computer using this FCI approach, which is a full configuration interaction approach. So sort of maybe the gold standard of quantum chemistry to compare to, right? So they want to compare their quantum solution to a well-justified quantum chemical result. Okay, so then they compare these two results essentially. And at this intermediate step here, what they essentially do is they write down this effective Hamiltonian for their active space. Right? So again, the active space here being, and maybe I can show you that, the NV center in diamond. So this is a defect in a host material. Again, you'll see the electronic structure of such a thing in a second. They use the orbitals of the defect, or the defect states of the defect, the electronic states of this defect as their active space. They write Hamiltonian for this active space, and then they solve that Hamiltonian either on a quantum hardware or on a classical full configuration interaction approach and compare the two results. I think that's the bottom line. And I think that's sort of, I would say, maybe Visha, you can disagree with me, but that's kind of what motivated us to look at such a workflow and try to apply that to a system, simply with the goal of characterizing how does it scale with system size, like where does it break if you make it system larger, and how does the noise affect the results. Now, they do that analysis for the NV center in this paper, right? So if you're interested in that, feel free to take a look. Okay, all right, so this is the bottom line. What Vishaya now does is, so she looks at aluminum oxide. So the motivation here is, I would say, actually comes from IBM, from our IBM collaborator. So they have projects they work on with companies that care about corrosion and aluminum corrosion, and the formation of aluminum oxide is important in that context. And so the ultimate material science goal may be that you want to mitigate corrosion. Now, if that was your only goal, we probably would not use quantum computers, right? We would simply just try electronic structure techniques to knowledge that we're building here. But again, we also want to learn about these IBM computers in this work. And so what I'm doing on this slide is, I guess, maybe two things. I'll show you the aluminum oxide unit cell real quick. And when we talk about corrosion, the way we will simulate this in this project is we're looking at defects in this. Maybe I can explain. And you expose that to air, so anywhere really. There will be oxide scale that forms on the top. Right? In other words, the aluminum reacts with the air, with the oxygen in the air, it oxidizes, and now we have this aluminum oxide scale. And at some point, the oxidation or the corrosion stops because this scale has now formed and it protects the base metal from further oxidation. Okay, so you can ask the question, and many people have asked this question, by the way, why does it work so efficiently, right? And one of the theories is that this diffusion through the oxide scale of more oxygen atoms from the atmosphere is not happening, right? So the oxide scale limits diffusion, then prevents corrosion through that. Okay, so that's sort of like the material science premise of this project. And I think we found I just want to, do a little bit of a advertisement for this paper, which has nothing to do with quantum computing, but we found that even studying that effect, ideal crystal aluminum oxide is unexpectedly difficult because a lot of these defect geometries that you need if you want to know where does oxygen go when it diffuses through this material are way more complicated than initially thought. So I think Alina found a bunch of defects that were not known before. No, sorry, not defects, defect geometries that were not known before. And that matters when you look at diffusion. Okay. What Vijaya did is she looked at the surface of the material because if diffusion happens, it starts, where the surface is. And so she took, let me see. Yeah, sorry for this blurriness. I don't know where that is. She took bulk aluminum oxide, which has these, it's in the alpha structure, the alpha aluminum oxide structure, has these lattice parameters, and turned that into a surface first, which means she repeated the cell twice in this direction, and I believe also 2 by 2 in the in-plane direction, and surrounded by vacuum. So this is your vacuum in our simulation. As a result, that's a classical computing result, but in terms of like getting this initial atomic geometry, as a result, the atoms near the surface relax. This matches actually more or less with the literature. So this is our starting point for a surface of this material, right? So this is what came out of discussions with Barbara that we want to, at IBM, that we want to look at how these defects near the surface form and what their formation energy is and what their electronic properties are. Okay, that's the premise here. So I think I said all these things already. Let me see. Yeah, so we want to look at the effect of the oxygen defects on the structural properties. I kind of mentioned that, but also on the electronic properties. And then we want to characterize how this works on a quantum computer. We use this quantum defect embedding theory to do essentially the approach that you saw on this slide here, but for the aluminum oxide surface with defects. Okay, so now last point, I said this many times now, but we want to look at how does it scale with system size and how does noise affect the results. Okay, so if you remember, this quantum embedding requires a distinction between active space and environment. And so the way Vijaya goes about this is we put a vacancy here. This may be our initial oxygen vacancy as one of the this is one example of various defects that she studied. I think it's the one with the most easy to plot electronic structure for a presentation. Anyway, so she puts the defect here. As a result, the atoms surrounding the defect relax. Okay. And as a result on the electronic structure of that changed atomic geometry, we see there is a defect level somewhere here in the band gap, maybe 2.4 electron volt. These are hybrid functional calculations. So this hybrid functional I mentioned earlier is what produced these results. We also see defect states here in the conduction band. So how do we know that these are defect states? We project we plot the partial electronic density of states arising from those energy levels here. And if we plot that in real space in a cell like this, we see that they're localized near the defect, right? So the state only occurs near the defect and not anywhere else. Okay, so now we'll use this to essentially get an idea what will our active space be. That's why I'm showing you these plots. We need to know which states are defect states, because for those defect states, we're going to solve this. We want to use this variational quantum eigensolver, not for the entire set of states. You can also see how many states. Well, I don't know if you really can see it, but just look at these. There's even more down here. There's a lot of states. So that's essentially the problem. Decide what is the active space. Okay. Now, how does that happen? So in the active space is done using by looking near your defect. Let me actually do that. There is a blue sphere here near your defect. And what we then do is we compute an integral for all the electronic states really, but we're trying to find states that are very localized within that spatial region that we call the active space. So this localization factor essentially determines the volume of the you integrate over the wave function. You integrate the wave function of your states over that volume, and you see how close you are to 1, right? If you're at 1, the wave function is entirely localized in it. If you're at 0.5, it's maybe not entirely localized, but 50% or something like that. Based on that localization factor, meaning states where the localization factor is high, that is the set of states that we then use to define our active space. So that follows essentially the Scully approach. Okay, so what does that now look like? So again, I want to show you, I'm trying to get to these results so you see what noise does and what these results look like in general. Okay, so then now we can pursue these variational quantum eigensolver simulations, and for that, Vijaya uses a set of orbitals that has essentially 2 electronic those along with their spins, and a unitary coupled cluster ansatz for the wave functions of these states. This is something we take from the literature, and Vijaya has done. I'm not showing this today because this is ongoing and preliminary, but we're also exploring, if this basis set is big enough and all these kind of questions. I think it's too technical for today. Vijaya is right there, right? We're happy to discuss this with you, but I'm trying to show you more like the effect of what happens when we do these simulations and what does noise look like. So we use these ansatzes from the literature and this quantum circuit, which I believe is also from the literature, and perform these variational quantum eigensolver simulations. Okay, this ansatz has single and double excitations included. All right. So the first set of results I would say are down here, where we plot the difference of the total energy that we get from the quantum approach, like this variational quantum eigensolver, and the classical computing quantum simulations, full configuration interaction simulations. So far, by the way, none of this is run on a quantum hardware. For these guys, there are simulators, right? The reason for that is quantum hardware is not cheap, and all testing, debugging, initial tests happen with a simulator on a classical computer that simulates the behavior of the quantum computer. Okay, so this plot still has that. You'll see real data in a second. And the other advantage is, in the simulator, we can turn noise on and off, right? So in other words, we can really see that by starting with a noiseless simulation of this approach, we indeed reproduce the full configuration interaction energy. So that comparison, I would say, is a sanity check, right? If yellow were to disagree from the zero line here, there's either a bug or some other problem, right? The convergence or something. We'd have to investigate before we go on any quantum hardware. Because if these two disagree, including noise is not going to make it better. Go ahead. Sorry, I should look in this side of the room also. Go for it. Two electrons, two holes, right, Vijaya? 2 electrons, 2 holes. Oh, sorry. Is that right, Vijaya? Do I quote you correctly? Yes. Right. 4 orbitals. 4 orbitals. 4. For this one. She did convergence. I removed the convergence figure from this talk because, again, I'm happy. Come over, we can talk anytime, but I just kind of, right. Okay. Right. Okay. So, yellow is no noise. And sort of like the good news here is that at least that reproduces the full configuration interaction result. And then we use this green curve here. This is a noiseless simulation still, right, Vijaya? This one particular curve. We come to the noise data on the real hardware on the next slide. So we simulate the noise on this system of IBM. So they provide this through libraries, right? You can download a library. They simulate the noise that get on certain of their hardware. They have all these names for their hardware, for the actual hardware, and you can simulate that. Magnitude. So in this case, this is unmitigated, meaning the error is there, but it illustrates maybe the order of magnitude of the error, and it also probably illustrates that we have to do something about it. I'll talk about the something about it in a moment. Before we do that, I want to show you the second result, which is now this Guadeloupe hardware from IBM. This VQE approach on the real IBM hardware. She ran, in this case, 4 independent calculations and uses that to produce sort of like error bars on these data points. And what you can see now is, again, noise affects the result, right? We're not at the zero line anymore, where these two results would be identical. Just to quantify, number one, the noise, and number two, also, how much does this change from run to run? I would say this red curve shows that. So this is we've seen this now for many different runs and many different cases. So I think this is a typical, I'm saying this with much less experience than when I called the BSE and experiment agreement good. But this is sort of like a typical situation that we see, that the noise gives us disagreements on the order of magnitude, and there is a certain scatter in the values. So the take-home message at this point, and maybe we knew this up front, but something needs to be done about this noise, right? It needs to be eliminated. And the way this is currently done on the existing hardware is so different. So there are different techniques, right? So one is called zero noise extrapolation. Okay. That's one of the ones we tested. But spoiler, we have no final answer yet, right? So you're not going to get a final resolution to all these problems. This is a snapshot of where we are. But the zero noise extrapolation technique works by, so if let's say if this is the circuit that you want to run, you introduce the inverse in another copy of the circuit, which in a noiseless system does nothing, right? Because they cancel each other to identity. But in a noisy system, just noise, well, this one will have more noise than this one, right? And if you do that with circuits of increasing size and you extrapolate to zero noise, meaning you extrapolate, in this direction, you should get sort of like to a zero noise limit. So that's the idea of this approach. The way you can do that is either through what's called global folding, where this entire circuit is simply replicated and inverted. You can see that here, or local folding, where these individual units of the circuit are replicated and cancel each other to identity in a noiseless system. So the idea is you artificially introduce noise and try to extrapolate to the zero noise limit. And by doing that, so then Vijaya compared this local folding, which did not really help, and the global folding. And in this case, we sort of mitigate / quantify error in this regime. So again, this is unpublished. It's not final. It's not complete. But that's sort of like the level to what we got, right? So the error before was maybe just above like maybe 0.4 electron volt here or something like that. And then we can get rid of that error within that range. The details, I think we're writing up as we speak, I guess. Okay. And before I conclude, I want to show you one other example. So because there is another interesting extension of this. So let's move now towards optical properties. Okay, so this is still total energies, right? You see this. This is the total energy of a system. If we want to look at optical properties, we need these electronic states. We don't need just the ground state, but we also need the excited states. And this is now what Yiting is working on currently. So he looked at this anthracene system. And the reason is for organic molecules, we don't necessarily need to use the full Bethe-Salpeter Hamiltonian that I told you earlier about, right? The one that has a rank of 50 to 500,000. But there is a model, which is this Frenkel-Hamiltonian for excitons in organic crystals. So our thinking was, if we have an organic crystal, maybe we can come up with a Hamiltonian that is smaller in rank. Okay, and by using this Frenkel-Hamiltonian. And so Yiting started doing exactly that. So he builds this organic crystal. In fact, this is not periodic, right? So these are really just 5 molecules. And what the variational quantum eigensolver would give you is this ground state. But we want, for optical transitions, we want to know also the excited state, right? And then also the oscillator strength for how likely is our transitions to happen between the ground state and a particular excited state. So that's what Yiting indicates with these X's here. Some of these states are not allowed to happen, right, by selection rules. And we want to know that too. But first, we wanted to know what the energies of these excited states are. Once you know them and you look at splitting between them, then you can hopefully compare to experiment. But I'm not sure if you're at that point yet. The problem that Yiting then Q only gives the lowest eigenstate usually, and he found, I mean, in the literature really, came up with this technique of variational quantum deflation, which adds a penalty term to access the excited state. So I put one figure here. This is what you do. So you add this penalty term here to the Hamiltonian. And then when you compute expectation values, you get this combined expectation value here. This is the Hamiltonian without the penalty term, and then this is the penalty term. And like before, the first term is evaluated on the quantum circuit, so the actual quantum hardware, and the penalty term is evaluated on the classical computer. So this is how Yiting has that implemented. And now let me show you some results for that. This is a busy slide, I realize that. Let's start with the noiseless result. This is, again, simulator without noise. And we compare the exact classical solution, classical computing solution. And what Yiting showed first is that by using this quantum deflation technique, we can get agreement with the solution that we know, which is computed on a classical computer, of these excited state as well, right? You can see now for maybe state 0 through 4 that these guys agree with what the result should be. So that's, again, that's not I would say a semi-success story. So if that was not true, we would have to find bugs in our implementation. Okay, so this works fine. And then and this is maybe where I'll stop in just a second. Yeating started running, and I think we have to look at the simulated pattern first, maybe. He started running on real hardware. Before that, he started to run on simulated noise on real hardware. And here you see now real problems again, right? You can see that in this case, these states seem to converge, but somehow not to the correct states, right? So our lowest energy state we defined with this approach converges more to something that's close to the energy of the first excited state. And this is due to noise, right? So I don't think we have a good explanation why they completely converge to still states that are found in the classical simulation. I'm not sure if we have fully resolved that, but in any case, they don't match with what they should match, which is everything should be one shifted down. So this is the simulator, and on the real hardware, we see a similar behavior. This is now real noise. The states converge, but not to the right values due to noise. This is, I think, what we're currently struggling with. So Yeating is developing schemes to mitigate that noise, and we're talking with Barbara because at IBM, of course, they're also trying to mitigate noise, and so we're trying to figure out a scheme that can work here. One interesting thing, at least for the computational people in the room, interesting thing is if you run on these types of simulations. This point, I think, is the important one. So this is not so simple, right? So we are used to submitting a job to a queue, and the job runs, and if there is a system maintenance, then the queue will be down and we cannot submit for 2 days and this kind of stuff. These quantum computers, so what happens there is they recalibrate these qubits all the time, right? So, and recalibrate, as far as I understand, is meaning people going into a room and doing stuff with the quantum computer. Again, look, for me, this is all Python, right? I don't see any of that. But talking to Barbara, so there is actual stuff happening as these simulations are running, right? So this is what he says here. So calibration happens during a running simulation. And what is the time scale of these calibrations? 4 to 8 hours, maybe, something like that. Like that like in intervals of 4 to 8 to 12 hours or something. So this happens pretty regularly. And the simulations that we're running run on the same order of magnitude, meaning in a given simulation, you encounter this kind of stuff and you don't really know it. So it just happens. It seems to, and I think, again, preliminary, we haven't published this yet, it seems to not affect actually our results so much, right? So the noise is there, so that's clear, but it's not that these calibration events are spikes in these plots or something like that. But we're at the level where when we tell these problems to Barbara, that she takes back to the people who built these queue submission systems, so that maybe whenever they calibrate, the queue is paused or something like that. So I think this is all super exploratory stuff, right? So this is, I know I presented here like, oh, we'll just run on a quantum computer. It's not exactly like that. So I think Vijaya and Yeating, they struggle a lot with this kind of very technical and very hands-on issues, I would say. Okay, so my conclusions, again, I said all of this is preliminary. None of this is published. So, don't spoil us at all or be super quick because we are trying to publish this. But so the take-home message, I would say, I hope you at least saw a few examples of techniques that people use on existing hardware to do material science-like simulations, right? So you saw, of course, very specific examples, but I think this quantum embedding is pretty general. This variational quantum eigensolver is also general. And now this quantum deflation to access excited states. Noise mitigation, again, this is not a surprise. So yes, I'm saying this here as a conclusion, but we knew that beforehand. Noise mitigation is a problem and we have to figure it out and improve. This is ongoing work. We looked at these 2 examples. And then I used the slide actually to put a bunch of resources. So I think there is a lot of interesting material. So if you're interested in doing either some of that stuff yourself or reading more about it, I put a couple of these resources here because I think not an exhaustive list, but I think there is a lot of very good documentation and getting started is actually not so difficult, I would say. So I think you can try that out with tutorials, with example notebooks and stuff like that. So IBM has good documentation. Other companies have that also. Okay. So I think this is just where I'll stop. And if you have any questions, I'm happy to answer. Oh, hold on. One. Halloween. So my group, Yeating, in fact, we came up with a couple. So this is a snapshot. This is not constructed. This is a snapshot from our Slack channel. So this is what could have happened, right? If Yeating would have gotten his will, but I refused. And so that's why I'm here. Just, I go back to the slide. Thank you very much. So yeah, any questions? I mean, I'm not we have also the experts in the room. Yiting and Vijay are right
We
here.
have time for a few questions. So.
How many qubits do you need to do something that you can't do otherwise?
I don't think I'm the right person to answer that. It depends on the details, right? So I think the estimates are, I can only quote what I hear from other people talking about it, because again, we're not in the regime to read that. But I think what thousands or tens of thousands, I think to get rid of noise on the hardware level. I think the noise right now is mitigated through these kind of schemes. To have a compute, like a quantum computer that inherently mitigates noise through qubits, I'm not sure what you actually would need. That's absolutely not my area of expertise. But a lot more than I think, even when we had IBM as a colloquium speaker, they were also careful about that, right? They said this is not going to happen that soon, I think.
Actually, you mentioned how long does it take to do these like iterative steps? You know,
so each iterative step, yes.
How long does it take?
Well, I would say, so Yiting, you and Vijay, you know the numbers. One of these simulations may be 12 to 24 hours or something like that. 6 hours, okay.
6 hours. And so you have to own the quantum computer for 6 hours? Wow.
It's crazy.
What's it doing for 6 hours? I don't, do people, anyway, I don't understand. I guess I don't understand.
Yes. That would be a question for, I don't know that number, but Vijay or Yiting probably know that number.
So it's just one that you keep running all the time, but it's the parameter that gets updated. So. Mm-hmm. Yeah. Yeah, it's one circuit. Yes, per set. Yeah. We have 3 parameters, for example. This one. Yeah. Okay.
And
another question if we got
come for lunch and have exactly this kind of stuff.
Good lunchtime conversation. Other?
I want to make this last question. What do you think's the next interesting thing you're going to be looking at with this hybrid quantum? Or what's the future like? That's really my question.
Well, you mean the future in my group or the future in general? Like, no, because I don't know. I mean, so I think for us, if we're staying in this optical space, like one of the problems, we would like to have somehow a quantum embedding approach that can start from this Bethe-Salpeter equation instead of this Frenkel-Hamiltonian, for instance. Have a way to look at optics in solids, for instance. I don't think we have made too much progress. In general, I think that's a very good question. Risk mitigation, I think, is the biggest problem right now.
All right, let's thank our speaker again and
Thank you.
Enjoy lunch.